Good morning. My name is Dina Demalawi, and today we'll go through histology of bone. Orthopedic surgeons are used to see bone, like seen on the left side image, with epiphysis, metaphysis, and diaphysis, while pathologists look at bone under the microscope and identify different. They see cartilage, they see bone marrow, they see bone proper with two types, a trabecular bone and a cortical bone. They also see periosteum and other structures that are associated with the bone. So the first video, I will speak about bone matrix. So bone divided into two things, cells and matrix. We'll start with speaking about the bone matrix. This is a section of bone taken from a child. This is how pathologists see bone. So the first thing about bone is to know that's formed of organic and inorganic substances. The organic substance is mainly represented by collagen type 1. Collagen type 1 is a protein, so on the routine stains that the pathologists use, it will stain red. So in this image, what we see red is here. And also, I'm moving my arrow, the carousel around. And also here, where it's highlighted with this red cloud. So here is red and here is red, and that's bone. These are pieces of bone, and because they don't have any blood vessels inside, they are trabecular bone. So when we look at it, it's all formed of pink material that's more or less homogeneous. Homogeneous means it's painted very well without spaces. But then someone can say, well, I see areas like here and in here where the pink staining changed to become purple. These are cartilage remnants within the bone spicules, and the reason for them is that this section has been taken from a child. And in children, the origin of bone originate from a cartilaginous formed skeleton that undergo ossification and becoming bone. So in children, particularly under the age of 5, during their infancy and up till the age of 5, their skeleton is transforming into bone from the cartilage, but there can be some remnants of the original cartilaginous skeleton hugged within the bone matrix. So this is a clue to tell me that this is in a child. And this is again a clue about what we'll speak in another video about the cartilage, and that the matrix of the cartilage is actually blue and purple instead of being pink as in bone. So to repeat, bone matrix is formed of two components, an organic component predominantly formed of collagen type 1, and it's why the bone matrix looks pink in color with the routine stains that the pathologist used. There is inorganic component which mainly formed of calcium and phosphorus that crystalline and form hydroxyapatite crystals. Calcium and phosphate hydroxyapatite crystals. This is the inorganic component. So when we focus on these bone spicules, we can see that there are white spaces that I'm circling over here and circling over here and here, and they have purple dots on them. Two of them are highlighted by these green arrows. These represent bone cells that are embedded and hugged within the bone matrix. These cells are called osteocytes, and we'll speak about them in details on the next video. But right now, we'll focus on the bone matrix, which is formed of this pink material. When we look at the edges of this bone spicule, moreover, it's very smooth in contour. It's not really irregular. Even this smaller bone spicule is very smooth in contour. When we look at the cells just lying at the surface of the bone spicule and are highlighted by the red arrow. They are formed of plump, oval cells that they are aligned as a single cell in row. So here is one cell, one cell, one cell, one cell, next to each other, but one cell, the thickness is just one cell, and go hand in hand along the length of the bone spicule. These are osteoblasts, and they are the cells that responsible for formation of the collagen type 1. That's the organic component of the bone matrix, and we'll speak about them in details on another video. So we spoke about osteocytes, osteoblasts, and bone matrix. That's pink. In children, we can have a cartilaginous remnant that's purple within the bone spicule. When we go further and leave the bone spicule and go around in the milieu in which these bone spicules or bone pieces are present, we find there is a lot of purple dots. The purple color, that very dense purple color, usually represent a nucleus of a cell, because the purple represent the hematoxylin part of the stain that the pathologist used, and it have affinity for DNA. So it stains the nuclei of the cells. So it means that away from this bone spicule, we have a lot of cells over here and over here. These cells represent the bone marrow. In children, the bone marrow is cellular and actively producing the blood elements. So these are the stem cells in the bone marrow and undergoing maturation, and then they will pour the mature cells in the blood to become red blood cells or white blood cells or platelets. So in children, the bone marrow is all populated by hematopoietic cells. So we see a lot of them over here. As we undergo aging and move to adulthood, the hematopoietic elements or the hematopoietic cells within the bone marrow only resides in the epiphysis and metaphysis of the bone, while most of the shaft of the bone doesn't have hematopoietic cells as it used to be when we were children. So what occupies the bone marrow instead of hematopoietic cells as we grow is fat. So here, this child is not infant, he's older, because we are starting to see some of these big white globules that are highlighted with an asterisk, with the blue asterisk over here. These represent fat cells. Fat cells contain fat. The problem, we don't see any color to the fat because it's washed out during our processing of tissue. Like pathologists, when they receive any tissue, it comes as soft or even bone hard tissue, and they have to cut very thin sections from, very thin in microns, like the measurement of these sections is supposed to be 3 to 4 microns, very thin sections. In order to do that, we have to transform this tissue to become more solid, or in case of bone, become more soft, but as well still solid, so we can have our thin slices. In order to do that, we use a lot of chemical material. During this processing, the fat starts to dissolve, but the space occupied by fat is returned and stained, and doesn't stain, but it appears as white globule. So this means that we had the fat cell here, this means that we have a fat cell here, this means that we have a fat cell here. Again, to summarize, this image was showing a section from bone. Type of bone is trabecular or spongy or cancellous bone. They are all the same meaning. It's in a child. The clue to identify that this is a bone is the pink matrix. the pink staining, homogeneous pink staining, which characterize the bone. There are cells inside the bone matrix, and there are cells just at the edge of the bone. Away from the bone, we can see a lot of cells which represent hematopoietic cells. These will be seen throughout the bone, whether it's shaft, diaphysis, metaphysis, if we're looking at a child. In adult persons, the hematopoietic cells stay in epiphysis and metaphysis only. We can see here we have white globules that represents fat. Now we're moving to bone again, but this section is from an adult. So the first striking thing, if we leave the bone, which is the pink material, the clue to identify the very homogeneous pink material of the matrix, we look at the surrounding as it's formed of this big white globules. All of them represents fat. I put a cloud inside one of these globules just to highlight that this is a fat cell. These are the boundaries of it. Okay. We don't see hematopoietic cells because this is from the shaft or the diaphysis of the bone of an adult. So all the hematopoietic cells have migrated and only stayed in the metaphysis and epiphysis, but not anymore in the shaft. When we look at the bone in an adult, we can see it have a pink homogeneous staining, which we have seen in a child. We don't see any cartilage in the center because that's an adult. So all the cartilaginous skeleton that was present in a fetus have already all transformed into bone. There is no remnants anymore because this is an adult and have been enough time that all the cartilage now in the bone have been transformed into bone. So all the matrix is pink due to the collagen, type 1 deposition. We still have cells inside the bone, and we can see one of them I highlighted with the blue arrow, and these are osteocytes, which we'll speak about in our next video, because now we're just focusing on the matrix of the bone. When we look at the surface of the bone, in contrast to children, the adult have only these flat cells, very flat cells, like as if just very small, thin line interrupted on the surface of the bone. These we call them bone lining cells or bone surface cells, bone surface cells or bone lining cells. These cells appear to be inactive, but there are evidence that they become active when the bone undergo the process of remodeling, which means that the bone start to form a new bone, eat the old bone, and form a new bone. And in contrast to what many people might think, that bone could represent just a constant organ that never change. Actually, our skeleton is always in a state of remodeling, that in an adult, within 5 years, we actually have a new skeleton. So this remodeling process is ongoing, that every 5 years, the skeleton of a person, of an adult, is renewed. It becomes a new skeleton through the process of remodeling, which involve bone cells. The bone lining cell is one of them. Bone surface lining cell is one of them. The osteocyte is one of them. The osteoblast is one of them. And we'll speak about this in detail in another video. The remodeling process happens so sporadic, like it doesn't say, okay, I'll use the femur, let's start with the femur, we finish it, we go to the tibia. It doesn't happen like this. It just happens very sporadic and in all bones at the same time, but at very small foci, that if I take a section from bone, from a healthy bone, the most likely thing I won't see it, or if I see, will be only a very small focus within the whole bone that's undergoing remodeling. Okay, so summarize, this is an image of bone from an adult. Clues that it's an adult. I have fat cells in the bone marrow, not hematopoietic cells, and we can see this with the white globules. I can see the bone doesn't have any osteoblast, none of the bigger cells that were next to the bone as we seen in the image of a child. Instead, we have these flat cells that we call them bone surface or bone lining cells. Okay. Next image, we'll look again at another section from bone, but we'll have a closer look on the bone matrix. We spoke that the bone matrix is pink, and we said this is because of the organic part with deposition of the collagen fibers. If we look at the bone closer, we can see that the pink matrix is really not 100% homogeneous. You can feel or you can see there is a tree park-like pattern. There is lines that are in parallel to each other. And these represent these higher pink next door to lighter pink, higher pink next door to lighter pink. The higher pink represent the collagen fibers, and the way the bone is formed, there is a particular arrangement of collagen fibers, and like this, bone is able to be very strong, but also is able to be resilient and doesn't break. So the collagen fibers, the architecture of the bone, is formed in a way that it enables bone to give you the support and hardness needed, but as well the resilience to be able to have this shock absorption instead of being brittle and break. So when we look at a mature, well-formed bone, which is supposed to be what's forming the adult skeleton, it's formed of bone matrix that show this parallel arrangement of collagen, and I'm going through the fibers just to highlight with the arrow over here and over here. And these collagen fibers are parallel to each other, and we describe them as lamellar. They show a lamellar arrangement. So each fiber has a lamellae, one line. The next one is parallel to it, another line. So they have a lamellar arrangement. This lamellar arrangement makes us name the mature bone as lamellar bone because it's able to have this particular arrangement of the collagen fibers which characterize the mature bone. The black arrow again highlight the bone lining cells, and the blue arrow highlight the osteocytes within the matrix. This is the same or similar, a different individual, but similar idea. It's a section from lamellar or mature bone in an adult. You can see the fat cells, you can see the pink matrix which characterizes the bone, and we can see the osteocytes, and we can see the bone surface cells. And I want you to focus more on the bone matrix. We can see the light and darker parallel lines of arrangement of the bone lamellae, which is due to the arrangement of the collagen fibers. And we can see even the osteocytes, these cells that are embedded, are kind of parallel with, they have as well certain arrangement in parallel with the lamella. I put two blue curves over here to show you that some of the lamellae start to be concentric and circular, but again they are parallel. So here, parallel, 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 right? The black arrow again highlights the bone surface cell, or lining cell. This is different, this image. When we look at it, we know it's bone because it is pink. It's very pink matrix, so it's bone. But there are different things about it compared to the lamellar bone we have shown. So number one, we can see that the bone lining cells are not there. Instead, we have this bigger, plump, ovoid cells. I have highlighted one of them over here with the black arrow and another one over here. But there are many of them, but each of them is a single row arranged along the length of the bone. These cells, when we look closer, they are formed of two parts, part that's pink and part is purple. Purple represents the nucleus, so the nucleus of this cell occurs at one side of the cell. It's not in the center part of the cell, it's on one side. And then the rest is formed by the pink cytoplasm. These are osteoblasts, and when we see them, it means that there is a new bone formation, right? So what we normally see just bone lining cells in an adult, but when we start to see osteoblasts, it means they are doing their function, which is bone forming. When we look at the bone here, it's formed of the pink material, but we cannot appreciate the parallel lines of the lamellae anymore. It's formed of this pink material without any lamellae can be seen. It still have the osteocytes, which we highlight with the blue arrow. This type of bone is called immature bone, and the second name for it is woven, W-O-V-E, woven bone. Immature bone can be seen in children. It's normally to see it in children. But if we see this woven, immature bone in an adult, it means a pathological process. It means a disease. It could be due to infection or inflammation, like osteomyelitis. It could be due to tumor, whether benign or malignant tumors, or it could be due to fracture. It cannot tell us what's the type of pathology there, but when you, the orthopedic surgeons, give us a biopsy or bone tissue, and I can see the age adult person, and then I identify woven bone, I know that there is pathology and there is disease there, even without looking at any imaging or hearing the history from you. Age, woven bone means pathology, if in an adult. In children, it's allowed because the skeleton is growing, and woven bone is the first step for bone formation. But as we go as adult, we're supposed not to see woven bone anymore. So there is an important implication to be able to identify woven from lamellar bone, because it means disease process in an adult. So we can use our regular microscopy, light microscopy, as pathologists to identify the difference. And really the difference that I don't see this nice lamellae. The other thing is that in woven bone, you feel there is more osteocytes within the matrix compared to lamellar bone, but this is very subjective, right? So we need more objective measure to differentiate between lamellar and woven bone. So that's why we have this additional piece on the left-hand side that's called a polarizable piece that we add to our light microscopy, and like this we have a polarizable microscope. What this piece do, it make the advantage of the collagen fiber being able to refractile. So collagen by nature can refractile, can reflect light, can make light bright using polarized microscopy. And because bone is formed of collagen type 1, so the collagen fibers can do this light, can do this refractile light, and through this we can assess the arrangement of this collagen fiber. So if we look at the right side of the image, we can see here we have the bone. I can see a little bit some arrangement of the lamellae, But in order to be sure, I'll use this polarizable microscopy, and I can see that the collagen is formed of this dark alternating with this light lines, and I can see that it has a nice parallel arrangement. Some of it in this direction, but some of it are more concentric. And that's how lamellar bone looks like. Woven bone, I won't have this lamellae parallel. See how nice they are? Very parallel over here, very parallel over here, and here, and even here. So that's lamellar mature bone. This picture, one on the left, that show by light microscopy, mature bone, lamellar bone, and on the right with polarizable light. So it's from the cortex of the bone. So the cortex of the bone is the shaft and the outer layer of the bone. And in contrast to the trabecular bone, which is formed with the thin spicules of bone, the cortex have blood vessels inside. So when we look at it, we can see blood vessels in part of it, and I highlighted one of them with a star, with putting a sun, black sun, and it represents the Haversian Canal. The Haversian Canal is where the blood vessels and sometimes nerves enter into the cortex of the bone. So they are spaces. Around them, the collagen fibers are arranged. And because the Haversian Canal is circular, so the collagen fiber have to be arranged in circle. And that's what we see highlighted in two blue lines around the Haversian canal over here. So we can see the Haversian Canal, and we can see the arrangement of lamellae around it. And this arrangement of the collagen lamellae around it, because it's in circle, we call it concentric lamellae. When you look at the right side, you have the same image, but under polarizable microscopy, you can appreciate the Haversian Canal, the space, as I'm pointing by my arrow, and around it, there is the concentric lamellae, which I drew two in blue line, but very nice over here. You can see the Haversian Canal, the space over here, and the concentric lamellae around. But as we have Haversian Canal, Haversian Canal, Haversian Canal, with the circles around, sometimes there is a space between each two concentric, or each four. You have even six because it's three-dimensional structure, right? Concentric lamellae, there is a space created. And this, again, filled by collagen fiber, but these collagen fibers are arranged just parallel to each other without forming a full circle, because there isn't a space for them to do the full circle. And this form the interstitial lamellae, and I highlighted with the red color 3 lamellae, but you can imagine the rest, and even here there is 2 lamellae, interstitial lamellae in between the concentric lamellae. Have to keep in mind that this arrangement of collagen fiber is crucial to enable the support and the resilience for bone. But also the cells inside the bone, which are namely called osteocytes, which we'll speak about in the next video, are arranged as well with the lamellae. So with the concentric lamellae, they are forming circle around the Haversian Canal, and the osteocytes with the Haversian Canal, with the arranged collagen fiber, they form the basic unit of metabolic, the basic metabolic unit of the bone, which is called ostein. And this will be described more in details when we go over physiology of bone with Dr. Smallman. This image, again, on the left hand is of woven immature bone, on the right hand with polarizable microscopy. Woven bone, as I mentioned, you don't really appreciate the arrangement of lamellae. You might tell me maybe there are here, but the majority of the bone I don't see any arranged lamellae. There is a lot of osteocytes. We can see it here. And when we use the polarizer microscopy, we really see, yes, there's collagen fibers. So we'll see this refractile fibers present, but they are like a haystack. There is no parallel. There is no specific arrangement. There is no circular or concentric arrangement. There is no parallel whatsoever. It's just a haystack of collagen. And this represents woven bone. And what do you expect? Do you expect with this arrangement the bone is strong or weak? The bone is very weak and is not resilient and can be easily broken because it's formed of haphazardly arranged collagen fibers. So are the cells. When you look at the osteocytes over here, they are just arranged any arrangement because they have no direction to go on. They have no lamellae to follow their pattern through. So woven bone, and on polarizable microscopy we can see the patternless arrangement of woven bone. Now I finished the first video, which we speak about bone matrix. Through this video, I aimed that we can identify woven bone, we can identify lamellar bone, we can know the difference between them, we can understand the implication when we identify woven bone in an adult. And I also tried to highlight the image of the bone arrangement, the collagen fiber arrangement within a mature bone. And also tried to make you all agree that bone matrix is pink, homogeneous structure, pink structure. This is very important to recognize it when we go to cartilage and to other tissue that are associated within the musculoskeletal system. So I put a few slides just for a quiz. So we'll start with the first one. The quiz here is asking, do you think that this image is of a mature lamellar bone or immature bone? So when we look here, do you think that this bone is mature or immature? You can say I'm not fair because I didn't give you the polarizable microscopy image, but that's a hard question. Then the other question on the same thing, on the same picture, these white globules, what do we call them? What do they represent? The third question is these cells intermixed with the white globules, these small purple cells, but a lot of them, what do they represent? This is next image, and because I didn't give you the polarizable microscopy, it's the same image I've seen, but a close-up on the bone, again, so you can answer me, is it a woven bone or lamellar mature bone? And this is the first video, and we'll go to another videos.